This is second half of lecture 16. In the second half, I would like to move a little bit past basic kinematics and think about more, slightly more advanced concepts. For example, how are the variables describing angular motion related to the variables describing linear motion? For simplicity, let's say we have a disk that's circular, and let's say this disk is rotating around its center with the rate of 1 revolution per second. If you think about this disk, it's made of many points. There are points close to the middle. There are points slightly further away. There are some points that are on the rim. All of those points are making their own circles as this disk rotates. And if you think about this, it's not very difficult to convince yourself that further away you are, the faster you move. And that's simply because this point on the rim, when you make 1 revolution, this point has to go all the way on this big circle, while this point that's closer to the axis of rotation has to move on a much smaller circle. So if you're further away from the axis of rotation, the faster you move. And if you use proper geometry, you can see this in your book. The exact relationship is that your angular velocity times distance from the axis of rotation is equal to your linear velocity. And this formula works if your angular velocity is in radians per second. So as you can see, further away you are, the faster you move. We have similar equations for the acceleration. Just to remind you, when you're moving on a circle, there are, in general, 2 types of acceleration. There is one acceleration that makes you spin faster. So if you're spinning faster and faster, then there is this tangential acceleration that does this. And there is the second acceleration, centripetal acceleration, that changes your direction and that keeps you on the circle. If you have a uniform circular motion where you're spinning with the same rate, then there is no tangential acceleration, and the only acceleration is the centripetal acceleration. Using exactly the same arguments, it's easy to convince ourselves that if you are further away, then you experience more acceleration as you move on the circle. And the exact formulas are, they are derived in your textbook. For the tangential acceleration, your tangential acceleration and your angular acceleration are related through this radius. So further away you are, more acceleration we experience. And for the centripetal acceleration, you have omega squared times r, where omega again is your angular velocity in radians per second, and r is how far away you are from the axis of rotation. Now I want to go over 2 problems. One of them is related to this topic, and the second problem is slightly more complicated. It involves a little bit of calculus. I'm not going to ask you to do calculus in your homework, but I think it's nice to do a quick overview of how calculus works with these concepts. So in one of your homeworks, by the way, you have, I think it's homework problem number 8, you have 2 disks that are interconnected. as they rotate by a belt. And every time you have this kind of problem where two rotating objects are connected by the belt, you know that what that means is that the linear velocities where the belt touches this gear, the linear velocities are equal. And from here, it follows that since velocity is higher, the further away you are from this, it follows that if you have a bigger gear, your angular velocity is lower compared to the second gear, which has a smaller radius. Anyway, let's move to problem 6.3. This is slide number 7. And in this problem, what you have is you have a gyroscope that has a wheel with a radius of 2.83 centimeters. So that's 0.0283 meters. This gyroscope starts from rest, which means that initial angular velocity is 0. It accelerates with 14.2 radians per second squared. And it does so until its final velocity is, angular velocity is 2,760 revolutions per minute. There are 3 questions. Question number A is, what is the tangential acceleration of a point on the rim of this wheel? So for this point, what's the tangential acceleration? What I will do is I will use this formula that relates tangential acceleration to the angular acceleration. A times r, alpha times r. I have to be careful when I'm using these formulas. I have to make sure that everything is in radians. I have my acceleration in radians, so that's fine. So for part A, what I do is I simply multiply 14.2 by 0.0283. And this will give me my tangential acceleration in meters per second. Meters per second squared. Sorry. In part B, I need to find the radial acceleration of the point when it's spinning at full speed. So the radial acceleration, which is the same as centripetal acceleration. And for this acceleration, we had the formula omega squared times r. Now here I have to be a bit more careful because my omega, my final omega is given in revolutions. And this formula only works for radians. So I have to first convert revolutions to radians. And I think it would be also nice to convert minutes to seconds. So I have 2,760 revolutions per minute. Each revolution is 2 pi radians, so this times 2 times pi. And each minute is 60 seconds, so I will divide by 60. And that's my omega in radians per second. So I will square this. I will multiply it by 0.0283. And this will give me my centripetal acceleration, again in meters per second squared. Okay, so now part C. In part C, I have to find what distance does a point on the rim move during the spin up. I can do it in 2 ways. One way is to find how much angle it covers as it spins and then convert it to distance. So why don't I do that? Let me do that. I know that if I have constant acceleration, then my angle is equal to my initial angle plus initial angular velocity times time plus angular acceleration t squared over 2. So let me say, for simplicity, that I started from 0 angle. I had 0 initial velocity. So this is 14.2 times t squared divided by 2. Now, all I have to do is I have to find how much time it took me to get from 0 angular speed to this much angular speed. I will do that by writing down what acceleration means. Acceleration is change in my angular speed divided by time. And from this equation, it follows that the time is change in my velocity divided by acceleration. Change in my velocity is from 27,000 to 0. It's 27,000. And my acceleration was 14.2. And actually, to be consistent, what I will do is I will convert this 27,060 to radians. So I will multiply it by 2 pi, and I will divide it by 60. Okay, so this is my time. I will put this time in here, and I will be able to compute how much angle I rotated by when I was accelerating from 0 to 2760 revolutions per minute. Once I know the angle, I can always relate my angle to the length. If angle is in radians, then the length of the arc is my angle times the radius. And this is the distance that I went, that the point on my rim traveled during this accelerated motion. Now let's do a problem 16.4. This is a problem that involves a little bit of calculus. In this problem, they tell you that the angular acceleration of a wheel is given by the formula 6 times t into power 4 minus 4 times t into power 2. They also tell you that initially, at t equals to 0, your angular velocity was 2 radians per second, and that your angular position, your initial angle, was 1 radian. We have to find angular velocity and angular position as functions of time. So to do so, we have to remember how acceleration, velocity, and angle are related. Angular velocity is derivative of the angle, and angular acceleration is derivative of the angular velocity. So to go from the angle to velocity and from velocity to acceleration, we have to take derivatives. And of course, to go back from acceleration to velocity and from velocity to angle, we have to take integrals. So then from this formula, it follows that angular velocity is integral over acceleration. And from this formula, it follows that your angle is integral over your angular velocity. We have acceleration. If we integrate it twice, we will first get to angular velocity, and then we will get to the angle. So let's do that. Let's integrate acceleration twice. Integral of 6t into power 4 minus 4 t squared with respect to t. Once is 6 over 5 t to power 5 minus 4 over 3 t cubed plus a constant that we don't yet know. Now so this is our velocity. Now let's integrate the second time to get the angle. So this velocity integrated over angle will give me 1 over 5 t to power 6 minus 1 over 3 t to power 4 plus c1 times t plus c2. This is my angle. So it looks like I found both my angle as a function of time and my velocity as a function of time. But I have these constants here, constant c1 and constant c2, and I have to specify them before my solution is complete. To specify them, I will use these initial conditions. I know that in the beginning, my velocity, my speed was 2 radians per second, and my angle was 1 radian. Let's start with this initial condition. So if my velocity in the beginning at time equal to 0 is equal to 2 radians per second, then this has to be 2, okay? Because when t is equal to 0, this term goes away. Sorry, yeah, this term goes away. I accidentally erased it. This term goes away, this term goes away, so this has to be 2. And then this also has to be 2 because it's the same constant, this constant here. C1 has to be equal to 2. And if I now look at this initial condition that my angle was 1 radian in the beginning, then in the beginning when t equals to 0, you know, this term goes away, this term goes away, this term goes away. So my C2 has to equal 1 radian. This now completes my solution. And my solution is that my angular speed is 6 over 5 t to power 5 minus 4 over 3 t to power 3 plus 2. And my angle is 1 over 6 t to power, sorry, 1 over 5 t to power 6 minus 1 over 3 t to power 4 plus 2 times t plus 1. So as you know, I'm running help room sessions on Monday, Wednesday, Friday from 12:30 to 2:30. If something in here is unclear, if you have further questions, please join the help room and I will try my best to help you. Now, before we stop this lecture, I want to very briefly touch on one object, and we will discuss this in more length in lecture 17. This is the concept of rotational energy. Before we talk about rotational energy, I want to remind you very briefly what the regular energy, kinetic energy means. As you probably remember, kinetic energy is mv squared over 2. And the meaning of energy is that if you have an object and if you want this object to have energy, you have to perform some work. And if an object has energy and you want to take it away again, you have to perform some work. So the meaning of kinetic energy is that it's the kind of the amount of work that it took to get this object moving. If you think about rotating objects, let's say we have something, a globe, something that rotates. Since this rotating object is made of small parts that are moving, it's obvious that rotating objects, even if they don't move around, have some energy. You know, you cannot just get something to rotate. You have to perform some work to make things rotate. And for kinetic energy, we had this formula where you had mass and velocity. And the meaning of mass is basically how difficult it is to make things move. And the meaning of velocity is how fast things move. And we will see that for rotating objects, we will have a similar formula for their energy. So let me write energy of rotation. And you will have something called moment of inertia times angular velocity squared divided by 2. It's clear why there is angular velocity squared here, because it takes more work to make things rotate faster. And this thing that we call moment of inertia or rotational inertia is kind of like mass. Objects that have higher moment of inertia are more difficult to rotate, and objects that have lower moment of inertia are easier to rotate. Again, we will talk about this more in lecture 17, but to give you a sneak peek, the moment of inertia of an object depends on two things. It depends on mass, and it depends on how far this object is from the axis of rotation. So, sorry. For example, if you have two spheres and they are identical, but one sphere is heavier than the other sphere, then the heavier sphere will be easy to rotate. Will be more difficult to rotate. Now, if you have two spheres, and let's say they have the same mass, so this is a sphere that has some mass, and this is another sphere that has the same mass, but the second sphere is hollow. Okay, so all of its mass is on the outer shell, and the inner part is empty. Then you may know this from everyday experience. This sphere will be more difficult to rotate than the first sphere, because even though they have the same mass, in the second case, the mass is further away from the axis of rotation. You can test these things. For example, if you have with dumbbells, it's much easier to rotate those dumbbells around this axis, and it's more difficult to rotate them around this axis, because for this first axis, the mass is closer to the axis of rotation, and for the second axis, axis E, mass is further away from the axis of rotation. Again, this is just to build some intuition. We will cover this more in depth in lecture 17. So before we break, I have a question for you. This is an intuitive question. If you don't get this, it's fine, but the question is based on what we have just talked about. Which disk is, do you think, easier to rotate? There are 3 disks on slide number 10. They are made of 2 parts, inner part and outer part. For disk number 1, the outer part is made of a denser material, and this is where you apply force. For disk B, inner part is made of denser material, and this is where you apply force. And disk 3 is kind of like disk 1. The denser material is outside, but you apply force here instead of here. So think about this question. Think about which one do you think would be more difficult to rotate, or to ask this question differently. After, say, 5 seconds, if I apply this force, which of the disks will be rotating faster? So let's pretend this is an iClicker question, and I will give you an answer to this question in lecture 17.